Loci is plural for locus. A locus means a set of points which satisfy a certain condition or property. So let's say we have two complex numbers, z1 and z2. The modulus of z2 minus z1 represents the distance between the points z2 and z1 on an Argand diagram. Let's show this. So I'm going to draw the real and the imaginary axes. Let's say that z1 is located here. So this is z1, and let's say z2 is over here. Now we can think of these 2 points, which are 2 complex numbers that have some real component and imaginary component. We can think of them as a position vector from the origin to that point. So this I'm going to label as a vector z1, and this is the vector z2. So it's the vector going from the origin to that complex number. Now let's draw what z2 minus z1 would be. What vector would that be? So in order to get from point z1 to z2, we need to go along the negative z1 direction and then in the positive z2 direction. So we went positive z2, negative z1, which is just the vector z2 minus z1. And if we draw that vector, it looks like the vector that goes from the point z1 to z2. So this vector is z2 minus z1. Now, these symbols either side represent the magnitude of this. So the magnitude is the length of this vector, z2 minus z1, or in other words, it's the distance between the point z1 and z2 on the Argand diagram. So once again, to summarize, this represents the distance between 2 complex numbers on an Argand diagram. Now, using this result, we can replace z2 with any general complex number which has the form x plus iy. We've now replaced that for z2. The points described by this expression gives us a circle with center x1, y1, and radius r. Let's see why this is the case. So this expression right here just tells us the distance between any general point, any complex number, and z1, because we showed that this represents the distance between z2 and z1. So this expression represents the distance between any complex number and z1, which is a defined complex number given by x1 plus I times y1. So let's say z1 is over here. Let me draw a diagram. Let's say z1 is located here, and this is x1 plus I times y1, and z is just any complex number, so it can be anywhere on this Argand diagram. It could be any of the points on this, because z just represents a general complex number. But this expression with the absolute value on either side, this refers to the distance between any general point and z1. And we have set this equal to r, so r is some fixed length. It could be 5. If this had been 5, then this expression refers to the set of all complex numbers such that the distance between those numbers and z1 is 5. So all of these complex numbers such that the distance between that complex number and z1 is 5. And we can see that all of those complex numbers that satisfy this condition will lie on a circle on the circumference where the radius is 5, and the center will be at the coordinates x1 and y1, since the center is at z1 and z1 has x coordinate x1 and y coordinate y1. So this expression, z minus z1, the modulus of this being equal to r, this represents a locus of points, so a locus is a set of all points, such that z will lie on the circumference of a circle which has radius r and centre at x1, y1. We can even derive the Cartesian form of a circle from this equation by squaring both sides. Let me write down z, which is just x plus iy, minus z1, which is x1 plus y1. So rearranging this, we end up with x minus x1 plus I times y minus y1. So I've just opened these brackets and then rearrange the terms. This equals r. Now we want to find the modulus of all of this. So in my previous video on Argand diagrams, we discussed how to find the modulus of a complex number. So if I have some complex number that looks like this, the modulus of z we can work out using Pythagoras' theorem. So here I'm just going to do the square root of x minus x1 squared plus y minus y1 squared. This equals r. Now I'm going to square both sides. And this looks like the Cartesian form of the equation of a circle, which you may be familiar with, where AB is the centre and R is the radius. And so we know that x1 and y1 are the coordinates of the centre of the circle, and R is the radius. Now let's look at the locus of points that are an equal distance from two different complex numbers, z1 and z2. So once again, I'm drawing an Argand diagram, and z1 is this, z2 is this. Let's say z1 is over here, and z2 is here. The locus of points that are an equal distance away from both of these points is what we're trying to find an expression for. Let's see, if I have a point located somewhere here, the distance from z2 to that point is quite short, but the distance from z1 is quite long. So this point is not an equal distance away from the two. Same goes for a point over here. This is not an equal distance away from the two. It's a lot closer to z1. The point over here, right in the middle of the line that joins these two, well, that would be equidistant from the two of them. The distance from z1 to that point is the same as the distance from z2 to that point. How about a point over here? Yep, that looks like it's about the same distance from both. We can do this for a huge set of points, and what we'll find is that the set of points that are equidistant from both z1 and z2 will form a perpendicular bisector of the line segment that joins these 2 points. So this red line, which represents the set of points that are an equal distance from z1 and z2, this line is a perpendicular bisector of the line segment that joins z1 and z2. Now let's see how we would write this down mathematically. So this represents the locus of points z on an Argand diagram such that the distance from z to z1 is the same as the distance from z to z2. So I've just stated all of this, but I've not actually shown why this line is the perpendicular bisector of the line that joins these 2 points, z1 and z2. Let's actually prove or show why this is the case. So I'm going to draw the similar diagram with points A and B, and I want to show that the set of points that are an equal distance away from A and an equal distance away from B, I want to show that they lie on the line which is the perpendicular bisector of the line which joins these two. So this is perpendicular. Now I'm going to label this point, which is the middle of the line segment AB, I'm going to call that the midpoint. Now we don't actually know that this is the locus. I'm just marking a midpoint M on the line AB. So since it's the midpoint, we know that AM equals MB. Now I'm going to pick any general point P, which is an equal distance away from A and an equal distance away from B. So if that is the case, then AP must be equal to PB. For example, if this is a point P, which is an equal distance away from A and an equal distance away from B, then this length PA will be equal to this length PB. Now, we can see that we've kind of got two triangles formed here if I connect M and P. I know that the side PM is common between both of these triangles. We also know that the other two sides, so this is the same as this, and this is the same as this. So we have two similar triangles, which must mean that all three angles are the same in both triangles. If these two angles right here are the same, so the two angles that lie on this line AB, so angle AMP and angle BMP are equal because they're two similar triangles. They are equal and they also lie on a straight line. They must both be equal to 90 degrees. So we've shown that that line is perpendicular. We can go the other way and prove that any point on the perpendicular bisector is equidistant from A and B, and I will link a proof to that in the description below. And because we've proved this both ways, since both directions of the proof hold, the locus of points with PA equal to PB must precisely be the perpendicular bisector. Now let's look at some examples of questions involving the concepts we've looked at so far. So, given that this complex number z satisfies this condition, we want to sketch the locus of z on an Argand diagram. So let's first draw a diagram. So if you remember, this looks like the form of a circle. So any complex number minus some complex number z1. The distance between those points equals some fixed radius r. This describes a circle with center x1 and y1. So let's first plot this point on our Argand diagram. So it's just 4. It has no imaginary component. 4 is just a real number, so we're just going to go 4 units along the real axis. So this is the center of our circle. It has coordinates 4, 0, or as a complex number it's just 4 plus 0i, which is just 4. Now the radius is 5, so I'm going to draw a circle with radius 5. So my circle has gone off the graph. So this distance is 5. So all of the complex numbers that lie on the circumference of this circle, the distance of them to this complex number is equal to 5, and that's what this expression represents. Now let's look at another example. We are given the condition that the distance between z minus 3 is the distance between z plus I. We want to sketch the locus of z and also find the Cartesian equation of the locus. So let's first sketch the locus of z. As we know, this will look like a perpendicular bisector that joins this point and this point. So let's first draw these 2 points, which are our z1 and z2. Looking back on our diagram, z1 and z2 are the points from which we are measuring the distance. So the first point, z1, is, if you remember, the form of this condition is usually given in this way. Our first complex number z1 is just 3. There's no imaginary component, so we'll just go 3 units along the real axis. This is z1. And our second complex number, z2, well, it's usually written in the form z minus z2, that represents the distance between z and z2. So let's rewrite this. So we can see our complex number is actually just minus I. This simplifies to this, but this is in the form z minus z2. So our complex number is minus I. Let's mark that on our diagram. So this point is z2. Now, the locus of z is the perpendicular bisector of the line joining these. So it looks something like this line. Let's find what the Cartesian equation of this line is. So the coordinates of z1 are just 3, 0, because it lies at the point 3 on the real axis and 0 units along the imaginary axis. z2 is at the point 0, minus 1, because z2 was just minus I. Let's find first the gradient of this purple line that joins z1 and z2. The reason why I'm finding that gradient is because the gradient of the line that's perpendicular to it will just be the negative reciprocal of the gradient of the line that joins z1 and z2. So the gradient of the purple line will be the rise over the run. So the rise is just 1 and the run is 3. So the gradient is 1 over 3. So the gradient of the perpendicular bisector will be minus 3. If you're unsure of how I calculated this gradient as 1 over 3, you can find the rise over the run by using these coordinates. But I've just observed that from this graph, this is 1 and this is 3. So the gradient of our perpendicular bisector is minus 3, and I know a point that lies on the line is the midpoint of this line segment. So let's find what that midpoint is. So to find the midpoint, I'm just going to take the coordinates of z1 and z2 and find the average of their x coordinates, which were 3 and 0, and then find the average of their y coordinates, which were 0 and minus 1. So the x coordinates were 3 and 0, and the y coordinates were 0 and minus 1. So this gives me 3 over 2 and negative 1 over 2. So that tells me the coordinates of the midpoint. Now I know the gradient of the perpendicular bisector and I know a point which lies on that line. So I can substitute it into the form of an equation of a line. So y is minus a half. This is a point which lies on the line, and I'm substituting it in so that I can find out what this plus c is. The gradient we know is minus 3. X is a point on the line 3 over 2. And now we're going to rearrange to find what plus c is, or what the y-intercept of this line is. So c equals 4. Let me plug all of the values we know into this equation. So the gradient is minus 3 and c is 4. So this is the equation of the Cartesian equation of the locus of points that are described by this condition.